Hey guys, my name is Hiraku Murakami, back with NovaEdge Academics. Today we'll be continuing with topic C. C1 specifically, simple harmonic motion. So we're done with topic A and topic B. We're getting into topic C, which is all about waves. And honestly, this is one of the most important topics. And it can get a bit challenging. So I hope I'll be able to break it down very simple for you. And for this video, let's nail the foundations. Okay, and so we're gonna start with topic C1, oscillations. So what is an oscillation? Probably you already know this from everyday life what an oscillation is, but it's just by definition a regular back and forth movement about the same central point. So a perfect example is a pendulum, right? So if I release the ball from here, it's gonna go back and forth, back and forth, back and forth. Same thing with a spring mass system. If I pull this mass to the right and release, it's going to go back and forth, back and forth, back and forth, right? You're actually going to learn later on that this, by definition, is called a simple harmonic motion, but we're going to say that for a bit later, okay? So why do we define oscillations? Well, it's because oscillations have certain characteristics that we can quantify. And the first two we're going to look at is period and frequency. By definition, period is a time taken for one single oscillation. So if I release the ball of the pendulum here and start a stopwatch and then measure the time for it to get back, that's one oscillation, right? Then that's the period. If I start from the middle, then it's the time to get back to the original position. So like that. If I start from the left, like that. That's one period that's one oscillation. The time taken is the period. Now the inverse of that, which is 1 over the period, is equal to something called the frequency. And frequency, by definition, is how many oscillations occur per second. The unit is called hertz, but it's actually just the same thing as per second. Okay? I'll explain this a bit later. Okay, so what do you think influences the period in these oscillations? Right, so for example, pendulum. If I was to trying to make a system that would have a longer period, meaning it would take longer time for this to come back, how would I do that? How would I achieve that? Well, probably your best guess is maybe we can manipulate the length, right? Maybe if I make the length longer, then it's going to take a bit longer to come back, right? That's one thing, right? You might be saying, what if I make this heavier, right? You're actually going to learn that mass in a pendulum system doesn't actually matter, but that's also a great guess. How about for a spring mass system? How about that? Well, probably it will have something to do with the spring constant, right? The stiffness of the spring. If I make it stiffer, probably it exerts a much stronger force. And if it exerts a much stronger force, it's going to go back and forth really fast, right? By the way, force, we've already covered this in Hooke's law, is proportional to K, right? Okay, well, what if I make the object heavier? That's probably going to make it a lot more difficult to push and oscillate, right? That's also another thing, right? Pendulum as well, right? Force is equal to mg. It's using gravity to go back and forth, right? So maybe it has something to do with the gravitational acceleration as well. Turns out those are true because these are the equations used for pendulum and spring mass system. You'll have this in your data booklet. Honestly, it's very easy. All you have to do is use your calculator, compute it, and plug it in. Okay, just note here that L here is the length in meters, and G is gravitational acceleration. If it's on Earth, it's 9.81, right? Here is the mass of the object, and K is the spring constant, which depends on things like material type, the geometry of the springs. Maybe it's coiled up more tightly, right? All of those stuff affect the spring constant. Okay, let's subtract this problem. So pause the video and give this one a try. Okay, so if gravitational acceleration is 9.81, then it's just plugging in. All you have to do is make sure that you convert length into meters. This gets me 1.86. B, let's just replace that with moon's gravitation. What do I get? 4.55. Part C, this equation predicts that the ratio of the time periods at two different locations is G1 over G2. Do your answers to A and B confirm that? Well, they do, but you actually have to be careful how you take the time ratio. It's actually T2 over T1 is equal to G1 over G2. The textbook doesn't specify which one is 1 or 2, so let's just take B to be 2 and A to be 1. So T2 over T1, so that's 4.55 over 1.86. This is 2.45. Let's try square root of G1 over G2. This gets me 2.45 as well. So these two will match evidently. Now, why do you say that I did T2 over T1 is equal to G1 over G2? Well, it comes with the derivation, if I divide the two, so T2 is equal to 2 pi L over G2. T1 is equal to 2 pi L over G1, right? So if I divide these two, T2 over T1 is equal to 2 pi L over G2, 2 pi L over G1, which after canceling out the top part, I get 1 over G2 over 1 over G1, which is same thing as G1 over G2. Okay, so that. A little quick math derivation that hopefully you can follow up with, okay? Now let's talk about amplitude, which is another quantity that we can quantify in oscillations. It's just the max displacement during an oscillation and is expressed as x naught. Okay, this is not the initial displacement. A lot of people get that wrong. This is the max displacement. Okay, which is called amplitude. And that's essentially here, right? If I just start from here, that's a max amplitude. That's how much max it can go. It cannot go further than that, and it cannot be less than that unless there's frictions and stuff like that, which in real life there is, but we don't assume there to be in this case. I'll talk a bit more when I come to energy in SHM. How does that look like in spring mass system? Well, it's the distance between the max displacement and the equilibrium position. You just have to be careful that you take the center. So it's actually like the displacement is here. That's how much it has moved from the original position to here. Or you can take the distance here, right? Doesn't matter. They should be the same thing, okay? Just be careful you don't do this to here. That's not the amplitude, okay? Now let's define what simple harmonic motion is. So this whole topic, C1, is called simple harmonic motion. So there has to be some significance to that, and there is. The definition of simple harmonic motion is a type of oscillation where acceleration is proportional and opposite to displacement. I'm going to say that again. Acceleration is proportional and opposite to the displacement. How do we express proportional? It's this guy. It's this thing. How do you express opposite? It's the sign. Okay? Negative means it goes in the opposite direction, right? This is probably the most important definition of this entire topic, simply because they will always ask you the definition of simple harmonic motion in your exam, 9 times out of 10. In paper 2, they will ask you to write in one sentence the definition of simple harmonic motion, and it's worth 2 marks, 2 easy marks. You cannot miss these 2 keywords, proportional and opposite to the displacement. Okay, well, what does that mean, you might ask? Well, let me show it to you. Suppose we have a pendulum system, and I want to graph the position versus time, or displacement versus time. Right, so let's do displacement versus time. So let's say I start from the max position and I oscillate back and forth. Okay, so I'm going to start from maximum displacement. Here, that's x naught, by the way. And then I'm going to go to the middle, s is equal to 0. And then go further, s is equal to minus x naught, right? So it's actually going to look something like this. And then, well, it's a cycle, so it's just going to keep going like that, right? So that's how it looks like, right? How about velocity? Let me change the axis to velocity versus time. Well, velocity at this position is 0, right? Because the ball is not moving. I'm just about to release it. So the moment I release it, what's the velocity of the object? 0. It's accelerating, of course, and it's going to increase its velocity until it gets to the bottom where it has the maximum velocity. So v is max here. And then it's gonna decelerate and then stop at the top. So v is equal to 0 here again. So it's actually gonna look like this. I'm just gonna complete the cycle. Okay, now you might be asking, why is it negative here? Because that's negative v, right? Why is it negative? Because velocity, the ball is going to the left. That's it. So while it's going to the left, it's negative. It's still negative till here. It's still negative till here. Okay, and then it turns around and comes back. So that becomes positive. Okay, now you might be asking, okay, what about acceleration? So let's do acceleration now. Well, acceleration at the beginning here, it's going to be accelerating downwards, right? Because of gravity. It's going to be accelerating downwards. In fact, it has a maximum acceleration, but it's at the maximum of negative, because which way is it accelerating? To the left, right? So acceleration starts here. And then, once it gets to the middle, guess what? It's no longer accelerating, because there's no more gravity. There's no more potential difference to push it to the center. So acceleration becomes 0. So it actually looks like that. So it becomes 0. And then while it's going to the top, the gravity is working against it. So it's going to be positive acceleration. And then come down and complete the cycle. So what do you notice here? Because this thing is A, V, and displacement. I hope you notice one thing, which is that displacement and acceleration is the exact opposite. When the displacement is positive and maximum, acceleration is negative and maximum. When displacement is 0, acceleration is 0. When displacement is negative max, acceleration is positive max, which means they are proportional to each other and they're opposite to each other. In fact, pendulum follows the simple harmonic motion by definition. Okay, so this is the definition of simple harmonic motion. I hope you understood. Okay, now this is also true for springs. Okay, so you can do the same thing for springs as well, where you imagine, okay, you start from here, you release it. What happens? It goes back, forth, back and forth. And the graph would look exactly the same. Exactly the same. Okay? Now here's the thing. Okay, so we know that acceleration is proportional to negative displacement. Okay, but I want to do it as A is equal to something times negative displacement, because that's going to help me quantify acceleration at each position. Well, that expression is here. So as long as I know x, I can calculate what acceleration it is at that point. Okay, now what is this w squared thing? That's the angular frequency. Okay, it's called angular frequency, and it's defined by this expression. You will have this in your data booklet again, but the unit is actually rad per second. Okay, and you might be saying, well, this looks quite familiar. These two looks familiar because we've already actually covered this in topic A. This is the same symbol and the same unit as angular velocity. In fact, they're actually related to each other. They're not the exact same. One is a scalar, one is a vector. So same way you have distance versus displacement, speed versus velocity, you have angular frequency versus angular velocity. If we can quantify the angular frequency, then I can find the acceleration at any displacement. Okay, perfect, right? So let's do a practice problem. So pause the video and give this one a try. Okay, so if we know the frequency, I can calculate the angular frequency, because the angular frequency is just 2 pi times f. So that's equals to 8.79 rad per second. Okay, and B, determine its acceleration when its displacement is 1 centimeter to the right. Always remember to convert it to meters. Acceleration is minus 0.77 meters per second. I can do that for this guy. Displacement is 4 to the left. So that's going to be Okay, and last but not least, it passes through its equilibrium position. At displacement equals 0, acceleration is also 0. Okay, so I hope you got the same answers as me. So last part about this video, we're going to finish up with energy in simple harmonic motion. The reason why is because, well, we've already covered energy before for kinetic energy, potential energy, gravitational potential energy, elastic energy. We've also covered thermal energy and all those stuff, right? Well, in oscillations, we also have energy change as well, conservation of energy as well. Now, what's happening is at the top here in the pendulum, you have gravitational potential energy. That converts into kinetic energy, and then that converts into gravitational potential energy again, right? Because pendulum, it falls down because of gravity, and so on and so forth, right? So there has to be some conversion of energy from gravitational potential energy to kinetic, back to gravitational potential, back to kinetic, back to gravitational. So this is what the graph would actually look like. So you have an energy versus time. So as I let go of the pendulum, first you have a lot of potential gravitational, then kinetic, potential gravitational, kinetic. And this is what it would look like. Gravitational potential, as it decreases, kinetic energy increases. As kinetic energy decreases, potential increases. And because there's a conservation of energy, the total energy remains the same. You're just converting from one form over the other. Now, of course, this is a very idealistic case, because if you have friction or air resistance, which we do in real life, then you're going to lose some of that potential energy and kinetic energy each oscillation. So it might actually in real life look like this. And potential energy might look like this too. Right? With each oscillation, the total energy is going to be decreasing at a certain rate. Right? But in IB physics, we try to keep it simple, so you won't take into account air resistance. We assume an idealized case, okay? Now, also we know gravitational potential energy is mgh. Kinetic energy is 1 over 2 mv squared. So we can also quantify these energy as well, as long as we know how much height has been covered here, the difference. And of course, if I know the velocity here, I can calculate kinetic energy and find the total amount of the total energy in the system, right? This is also true for, not for pendulum, but for mass spring system. For mass spring system, you're replacing gravitational potential energy with elastic potential energy, because now the force pushing the mass spring system is no longer gravity, but this guy. Right? Hooke's law. We've already learned this before. So gravitational potential energy, you can replace it with this guy instead. Okay? So let's do a practice problem. So pause the video and give this one a try. Okay, so the pendulum swings from the right and comes back and forth, right? So the middle position will look like this. They're saying the height difference here is 5 centimeter. Okay, so let's do this problem. So we know at the beginning you only have gravitational potential energy. So that's actually the total energy of the system. So maximum potential energy is equal to mgh, which is 0.1 kilogram times it by 9.81, and you should get 0.049 joules. Okay, make sure everything is in SI units. So for example, 5 centimeter, you need to convert that to meters. Grams, you need to convert that to kilograms. Okay. Sketch a graph with fully labeled axis to show the variation in potential energy of the pendulum in the first 1.6 seconds after it was released. Well, I'm not drawing it to scale, but we can try. Energy. So potential energy is going to go like this. Okay, now they're telling me for the first 1.6 seconds. So let's find the period. So the period is equal to 1 over f. So 0.8 seconds. So for one period is 0.8 seconds, 1.6 seconds here. Okay, so I can actually erase this part because they only wanted the first 1.6 seconds. Okay, now if I were to draw kinetic energy at the same time, it would look like this as well. Determine the maximum speed of the pendulum. Well, I can do the same thing, conservation of energy, right? So this has to also be equal to kinetic energy at this point. So kinetic energy. So rearranging this, I get V is equal to okay, and we're gonna finish the video here. Next video is going to be HO topic. So if you're in SO, then you don't need to watch that. But honestly, I highly encourage even SO students to watch those videos as well, because it will give you a better understanding of everything overall. You won't need it for the exam, but it doesn't hurt to learn and know more things in IB physics. It will help you connect some of the dots in standard level as well. Okay, so yeah, we'll see you in the next video. Hey guys, thanks for watching. If you like this kind of video, then consider giving us a like and subscribing to our channel. We have a lot more lecture style video and content like this in our channel, so feel free to go check it out. If you're looking for additional guidances like one-on-one tutors in IB subjects, SAT, TOK essay, IAs, writing, etc., then go to our website at NovaEdgeAcademics.com, fill out the form, and we'll get in touch with us. In the meantime, we'll see you in the next video.